you so much to all the organizers for this excellent opportunity to present our work. My name is Oscar Macias. I am currently a postdoctoral fellow at the Grappa Institute, University of Amsterdam, and this work is done in collaboration with Martin Paul, Faira Coleman, and Chris Gordon. So in this analysis, we present a new model for hydrogen gas in the center of the galaxy, and then evaluate the impact of this new model on the characteristics of the galactic center axis. All right. So already Silvia gave a very nice overview of the status of the galactic center axis. So I'm going to draw from her talk a lot. So essentially, basically, let me emphasize a point that Silvia already nicely explained, and is that when we observe the gamma rays from the center of the galaxy with Fermi-LAT, we realize that the strongest source of gamma rays from this region of the sky are the gas-correlated gamma rays. So basically, this is the gamma rays that results from the interaction of cosmic ray particles with interstellar gas in the galaxy. So if you compare this component with the galactic center axis, we realize that depending on the energy, this gas-correlated component is can be orders of magnitude stronger than the galactic center axis. So the idea is that if there are potential artifacts or defects on our gas models, then they can impact potentially the characteristics of the galactic center axis. And that's basically the focus of our work, right? So let me basically summarize here what has been done. So what I'm showing here are the hydrogen gas that are constructed by the Fermi-LAT collaboration. These gas are divided in different galactocentric rings. So this is done in order to model the cosmic ray diffusion in the galaxy. And these gas are the official version of the hydrogen gas for analysis of gamma rays. These are very very suitable for analysis away from the center of the galaxy. But these gas maps do contain a few caveats that become important in the center of the galaxy. So one of the caveats is that in the construction of these gas maps, they assume that the gas follows circular orbits in the galaxy. Now, this assumption breaks down in the center of the galaxy because of the strong gravitational potential of the galactic bar. So the galactic bar induces highly non-circular orbits for the gas in the center of the galaxy. So we have tackled this problem in previous papers by using hydrodynamical simulations. Now, another assumption that goes into the construction of the official Fermi gas maps is that they only model hydrogen line emission. Essentially, they neglect the strong absorption lines in the center of the galaxy and continuous hydrogen emission. And so basically, what we do here is to properly construct gas maps that properly account for absorption signals and continuous hydrogen emission, right? So we do this by solving the radiative transfer equation and accounting, as I mentioned, for this continuous emission and the absorption lines. So what you see here is an example just in the line of sight towards the supermassive black holes, Sagittarius A star. You see these very strong absorption signals in the hydrogen gas. And so the black shows the observation, and we show our results for two different models, assuming 200 Kelvin for the excitation temperature of hydrogen and 400 Kelvin for the excitation temperature of the hydrogen. And so we show here that our model does a reasonable good job at explaining these strong absorption signals in the direction of the center of the galaxy. Now, what this implies is that the old models, so this is an image of the center of the galaxy. This shows the old model of hydrogen gas in the center of the galaxy compared to our new model that accounts for hydrogen absorption. And what we find is that essentially there was missing gas in the previous gas models used in the analysis of the galactic center axis. So you see that compared to this model, we find stronger gas. So there was missing gas material in the previous model. And so we want to understand what is the impact of this missing gas on the characteristics of the galactic center axis. So what we do, as Silvia explained, is basically ask the question, where the galactic center axis, I mean the spatial morphology of the galactic center axis, is correlated with the stellar mass in the galactic bulge or with any of the dark matter distributions that are predicted by embodied simulations. And our results of these statistical tests are shown in this table. So it's a little bit of a busy slide, so let me walk you through it. So essentially, we feed the data with the astrophysical model that contains the new hydrogen maps. So these also contain inverse Compton point sources, etc., for this region. Now, we ask what's the significance of adding one of these new templates that is supposed to explain the galactic center axis. And so we sort these in order of their significance of these templates, and we find that this model called the nuclear bulge, so the stars in the inner 200 parsecs of the galaxy, is really wanted by the data. So it has a very strong significance, and so we add these to our model. And then we repeat this analysis. We add this template to the model and ask again what is the significance of these GCE templates. And so what we find is, which is very striking, is that once you add the nuclear bulge with the new gas maps, there is no longer significance for significant detection for any of these dark matter templates. And but still, we find that the boxy bulge template, the stars in the inner 10 degrees of the galaxy, are still needed by the data. So we again add this template to the model and repeat the procedure. And again, we confirm that there is no need to include any of these characteristic dark matter templates in the model. So that this basically supports the stellar explanation for the galactic center axis. And again, this favors the dark matter explanation using these new hydrogen maps for the center of the galaxy. Now, the next question that we can ask is where there are potential biases in our likelihood results. And so we evaluate this using the Bootstrap method. Essentially what we do is we take the best fit parameters for our best fit model. So this model here that includes the stellar templates. And then we create mock data from taking Poissonian draws from the best fit parameters. And then so we create hundreds of mock data, and we fit the mock data with the same statistical tools that we use for analyzing the real data. And so the results of these Monte Carlo simulations are shown with these Brazilian bands, and the results of the log likelihood values for the real data are shown with this dash line. And so basically this shows that the log likelihood values that we get in our statistical analysis agree with Monte Carlo expectations. So that's a sanity check that our analysis, our galactic diffuse emission is passing. Now, the next question is where our new models, including this new hydrogen gas, are better. So we create, so where we have a galactic diffuse emission model that is better than what we had before. And so here we compare, this is the test statistic for different versions. We create different gas maps assuming different spin temperatures. And we show here that the significance that, well, so that this map is much better than the previous model that was claimed to be the best in the literature. So we are definitely doing much better than we had before. So it's just because we are including more data. So basically data that was missed before, this absorption line data that was missed before, now we are including it. And so therefore we have a better gas model for the galactic center. Now, the next reasonable question to ask is whether this is the last word on the galactic center axis, where we have solved completely the puzzle. So what we do to analyze this question is to create the residuals. And so basically we compare the data against our best fit model. And what we find is that we still have some correlated residuals that, and basically, so we don't yet have residuals that that agree with Poisson noise, essentially. So we don't yet have Poisson noise in the residuals. So what that means is that even though we have given a step forward in the right direction, we have better gas maps, these maps still don't fit the data at the Poisson noise level. So there is still work to be done. Okay, so then I get to the conclusions of my talk. So essentially, we have constructed a new hydrogen gas for the Galactic Center that accounts for absorption and continuous emission. We still confirmed with these new gas maps, confirmed the stellar bulge explanation for the Galactic Center excess. We again find that there is no need to include any dark matter template in the for the Galactic Center excess. We find that our likelihood values agree with Monte Carlo expectations, but we don't yet fit the data at the Poisson noise level. Okay, so that's me, and yeah, I'm happy to discuss or receive feedback from you. Thanks a lot.